This is video number 3 in Mr. Sweeney's AP Physics C class, and today we're going to be discussing Newton's third law of motion. And Newton's third law of motion states that for every force that acts on an object, there is a reaction that is equal in magnitude and opposite in direction. So if there's a force applied to something, it must be that there is an associated force in the opposite direction. Because of this, we can state that forces will always come in pairs. There's the original force and there's the reactionary force. And it's the object itself, the one applying the force to whatever it's applying it to, that has the force applied, the reactionary force applied back on it. An example of this would be if you kicked something or if you ran into something, you would feel that on your foot or wherever your body made contact as a reactionary force. So kicking, punching, running into something, this is why that can be uncomfortable for us. Let's try a couple of examples, just looking at how this force, this reactionary force due to Newton's third law works. In this first example, a 0.25 kilogram book rests on a table. What I want to know is what is the normal force that's applied to the book by the table. Remember, normal force is a reactionary force that is applied to an object as it rests against the surface. So this book is resting against the surface. It's going to place some amount of force on the table. The table will have a reactionary force that is placed upon the book. So to start this problem, instead of looking at normal force directly, we're going to try to analyze this problem by looking at the gravitational force that's acting on the book and pushing against the table. So we're going to do that. Force of gravity equals mass times acceleration due to gravity. And our mass is 0.25 kilograms. And our force of our acceleration due to gravity is a negative, meaning pointing downwards, 9.8 meters per second squared. Solving this for force of gravity, we find that our gravitational force that's acting on the book is a negative 2.45 newtons. If we're looking at this as a free body diagram, we would represent this force of gravity acting on the book as a vector pointing directly downwards. Force of gravity equals negative 2.45 newtons. And we can represent the reactionary force, force normal, as a vector pointing in the opposite direction. The book is at rest on the table, meaning that it's in equilibrium and all forces cancel each other out. So force normal must equal force of gravity in magnitude, but with an opposite direction. So force of gravity is negative, force normal is positive, positive 2.45 newtons. Let's try one more example on Newton's third law. And this is an example that is modeled after an actual AP Physics C problem. In this problem, it states that two blocks are pushed along a horizontal frictionless surface by a force of 15 newtons to the right. And this is shown below. The force that the 2 kilogram block exerts on the 4 kilogram block is what? We're trying to figure out the force between the two blocks. The one block's pushing on the other block is pushing back on it. Note that the force between the two blocks is not 15 newtons. So it's getting 15 newtons from the left, but the 4 kilogram block is not placing 15 newtons of force on the 2 kilogram block. So in order to approach this problem, we have to be able to separate and isolate one of our two blocks so we can draw a free body diagram for that block and determine what force is being placed on it. Now, the two blocks together, the 4 kilogram and the 2 kilogram block, will act as a pair. So when they're pushed together, the 15 newtons there will push both blocks as one system. So we can find what the acceleration of the system is, but first we need to add the masses together. So the mass total of the system is equal to the mass of the 4 kilogram plus the mass of the 2 kilogram blocks. And that gives us a total mass of 6 kilograms. From here, we could find the acceleration of our system using force equals mass times acceleration. The net force placed on the system equals the mass of the system times the acceleration of the system. And plugging in these values, 15 newtons equals 6 kilograms times acceleration, we find that we have an acceleration of 2.5 meters per second squared. Now, having found this acceleration, 2.5 meters per second squared, both the 4 kilogram box and the 2 kilogram box are both accelerating at 2.5 meters per second squared. But a 15 Newton force applied to either one of these boxes would produce a much larger acceleration. So the force is getting distributed between the two. It's acting on it as a whole, and there's some force between the two of them that obviously must be pushing on the 4 kilogram box in order to keep it from accelerating at that rate. So let's isolate this 2 kilogram box. For the 2 kilogram box, this states that the net force of the 2 kilogram box must be proportional to its acceleration. Now, as part of our system, our acceleration that's on this box must be 2.5 meters per second squared. Even though the force, we're not certain about what net force is on the box, we know its acceleration, so we can find this net force. Just multiply the mass of the box by the acceleration it's undergoing to find the net force acting on the box of 5 newtons. So that means there's 5 newtons acting on the box. It must be applied by the 4 kilogram box in order for that to accelerate this 2 kilogram box. So this shows that the 4 kilogram box is accelerating the 2 kilogram box by pushing on it 5 newtons. If we took the perspective of the 4 kilogram box, we can say that the net force of the 4 kilogram box must be the same as the 2. We multiply the mass of the 4 kilogram box by 2.5 meters per second squared, and that is 10 newtons. So the 2 kilogram box is getting with a net force of 15. The 4 kilogram box has a net force of 10. The total net force on the system is 15, getting distributed between the two boxes. And if we draw a free body diagram of this, initially we pushed on the box with a 15 Newton force, but then between the 2 kilogram and the 4 kilogram box, there was 5 newtons of force. That's what we found in our previous step. And this makes sense because you push on it with 15 newtons, the 2 kilogram pushes back on the 4 kilogram box with 5 newtons, giving a net force on the 4 kilogram box of 10 newtons. And that makes sense with our acceleration of 2.5 meters per second squared. This is it for video number 3 in dynamics.